let's now talk about another concept called moment of inertia. Moment of inertia. A very important concept in rotational motion. Well, I'm going to develop that by taking a disc like this. Now, suppose I have a disc that I want to rotate. You can see I can rotate this disc about this axis. Look at that. This is the axis. And if I apply a torque, I'm applying a torque and rotating the disc. Now, when this disc rotates, every point object on this disc can be considered to be made up of thousands and millions of particles. And we can consider the motion of each of those particles. Each particle will be subjected to a force, and that force will produce an acceleration. Alright, let's look at that in a little more detail. Now, here is the disc that I have just been showing you. Consider a disc of mass m and radius r rotating about an axis. So the disc is rotating about an axis. Can I say the disc is rotating in the clockwise direction? I hope you understand that. The direction of rotation is the direction of motion of the hands of a clock. So the disc is rotating in the clockwise direction. A point mass m1 at a distance r1 from the center. Let's say this is a point mass of mass m1 and its distance is r. We have a point mass m1 at a distance r1 from the axis. If a force F1 is acting on that mass m1, that force F1 will produce on it an acceleration a1 according to Newton's second law of motion, F net equal to ma. Is that right? So a force F1 acting on this mass m1 produces an acceleration a1. This force F1 produces an acceleration on this mass given by F1 equal to m1 a1. Well, if alpha is the angular acceleration of the disc, when the disc is rotating, it will have an angular acceleration. If alpha is the angular acceleration, you know how it is related to linear acceleration. You know that A equal to R alpha. So A1 equal to R1 alpha. Therefore, we can say F1, the force acting on this point particle, is M1 R1 alpha, where M1 is its mass, R1 is the distance of the point from the axis of rotation, and F, the force, is at right angles to that distance. Alright, what is the torque of this force about this axis? Tell me, what is the torque of this force F1 about this axis? It will be the torque arm, which is R1, times F1 sine theta. Theta is 90 degrees, therefore sine theta is 1. So we can simply write it as tau 1. Tau 1 will be the torque on this particle. Will be R1 times F1. So tau 1 is R1 times F1. Now remember, the sine theta becomes 1 because angle theta is 90 degrees. And replace this F1 by this quantity. F1 is M1 R1 alpha. So that will be R1 times M1 R1 alpha, and that will be M1 R1 squared alpha. This is the torque on this minute particle of mass m1. That means if you now take any other particle on that rotating disk, there will be a similar torque on that particle. So let's consider now another particle, a force F2 acting on a point mass m2. This is a point mass m2, and a force, now this m2 is at a distance r2 from the axis of rotation. A force F2 is acting on it. What is the torque on this particle? It will be R2 multiplied by F2. Is that right? Tau 2, the torque on this particle, well, the torque is rotating that particle, will be R2 times F2. And what is F2 equal to? If F1 equal to M1 R1 alpha, then F2 will be M2 R2 alpha. Will alpha be different for these two particles? We had talked about it earlier. You see, because the radius rotates, as the radius rotates, it describes the angle. That means the acceleration, the angular acceleration of any particle on the disk will be the same. Why? Because all the particles describe the same angle in a given time. Therefore, this mass m2 and this particle of mass m1 and any other particle on the disk will all have the same angular acceleration, which is alpha. So the mass of the particle may change. The mass of the first particle is m1, the mass of the second particle is m2. The first particle is at a distance r1 from the axis of rotation. The second particle is at a distance r2 from the axis of rotation. But the angular acceleration of any particle on the disk is all the same, namely alpha. So tau 1, the torque on the first particle, is m1 r1 squared alpha. Tau 2, the torque on the second particle, is m2 r2 squared alpha. The torque on a third particle will be m3 r3 squared alpha, and so on. If you now take an ith particle, what's an ith particle or nth particle? The torque will be mi ri squared alpha. Let's write that down. The disk is made up of thousands of such point masses. If tau I is the torque on the ith particle, well, for this particle that I equal to 1, for this particle that I equal to 2, that I can have any value. If you take the 100th particle, then that I will be 100. So if tau I is the torque on the ith particle of mass mi, what will be tau I equal to? Tau I will be mi ri squared alpha. Okay. The total torque, therefore, will be the sum of the torques of all these particles. Is it not so? Does it make sense? I think so. The total torque tau on the disk. We have now obtained the torques on each individual particles. If you know the torques of all the particles that compose the disk, then the total torque tau on that disk will be the sum of all these torques. How do I write it? Tau equal to tau 1 plus tau 2 plus tau 3 plus tau 4 and so on all the way to tau I. Depends on how many particles are there. and we can write it like this: tau equal to summation tau I. Summation tau I. Add all the torques on all the particles. That will give you the total torque on the disk. Alright? And this tau I is mi/ri squared alpha. So we say tau, the total torque on the disk, is summation I mi/ri squared alpha. What does this mean? It means m1 r1 squared alpha plus m2 r2 squared alpha plus m3 r3 squared alpha all the way to the last particle. Now, you know that m and r are different for different particles, but alpha is the same for all particles. The angular acceleration will not be different. They will be the same for all particles. Therefore, I can take this alpha and keep it outside the summation. So I can write it as alpha times summation I mi/ri squared. And now, this quantity summation I mi/ri squared has great significance in rotation. What is the significance? Summation I mi/ri squared is called the moment of inertia of the disk about the rotating axis. Now there are a couple of information that's important there. Moment of inertia of a rotating object is always measured about an axis. You see, the moment of inertia of this rotating disk, the expression here, summation I mi/ri squared, is the total torque of the whole disk about this axis. You see, this is the axis of rotation. If you want to take the torque of the same disk about another axis, it will be different. You see, the moment of inertia of an object is defined about an axis. If you change the axis, the moment of inertia will change. Well, I will show that in a minute. So what is summation I mi/ri squared called? It is called the moment of inertia of the disk about the axis of rotation. What is the unit for moment of inertia? Moment of inertia is represented by I and is measured in kilogram meter per second squared. So, let me ask you, if a point particle is rotating about an axis, if this point particle m1 is rotating about the same axis, what is the moment of inertia of this particle about that axis? The moment of inertia of this particle about this axis is m1 r1 squared. The moment of inertia of this particle about that axis is m2 r2 squared. And add the moment of inertia of all such particles. That is what we call this. Summation I mi/ri squared is the moment of inertia of the disk about its axis of rotation, and it is measured, look at this, kilogram meter squared is the unit of moment of inertia. We can now write an equation for torque I. Now look at this, torque, we have the equation torque equal to alpha, the angular acceleration, multiplied by this quantity. What is this quantity called? This quantity is called the moment of inertia, and we will represent it by the uppercase I. And therefore, I can now write tau equal to, this is called I, that will be I times alpha. And that is the equation